Welcome to Chapter 1 of the Introduction to Nanomaterials series. In this lecture, we'll explore the fascinating world of materials at the nanoscale. We'll learn what makes nanomaterials unique, how they're classified, and the fundamental equations that describe their behavior. By the end of this chapter, you'll understand why a gold nanoparticle can be red instead of gold-colored, and why materials behave so differently when they shrink to just a few nanometers. Nanomaterials are materials with at least one dimension between 1 and 100 nanometers. To put this in perspective, a nanometer is 1/1000th of a meter. A human hair is about 80,000 nanometers thick, a red blood cell is 7,000 nanometers, and DNA is just 2 nanometers wide. At this scale, materials exhibit unique properties that differ dramatically from their bulk counterparts. Gold nanoparticles appear red or purple instead of gold. Silver and gold particles scatter and absorb light at wavelengths their bulk metals never do. And the same material can switch from chemically inert to strongly catalytic simply by being made small enough. These extraordinary properties arise from two key phenomena: quantum confinement and surface effects. While the term nanotechnology is modern, humans have unknowingly used nanomaterials for centuries. The Lycurgus cup from the 4th century contains gold and silver nanoparticles that make it change color when lit from different angles. Medieval stained glass windows get their brilliant colors from metal nanoparticles. Damascus steel blades have been reported to contain carbon nanostructures, though this interpretation is still debated. The scientific era began with Michael Faraday's synthesis of colloidal gold in 1857. Richard Feynman's famous 1959 lecture, "There's Plenty of Room at the Bottom," envisioned nanotechnology. The invention of scanning tunneling microscopy in 1981 let us see atoms for the first time. Fullerenes were discovered in 1985, carbon nanotubes were reported in 1991, and graphene was isolated in 2004. Fullerenes and graphene each led to a Nobel Prize, in chemistry in 1996, and in physics in 2010. Two fundamental phenomena make nanomaterials unique. First, quantum confinement. When a material's dimensions approach the de Broglie wavelength of electrons, typically a few nanometers, the electrons become confined like waves in a box. This quantizes their energy levels, leading to discrete states rather than continuous bands. The result is size-tunable optical and electronic properties. Second, surface effects. As particles shrink, the fraction of atoms at the surface increases dramatically. Surface atoms have fewer neighbors and unsatisfied bonds, making them more reactive. This leads to enhanced catalytic activity, lower melting points, and increased chemical reactivity. The surface-to-volume ratio follows a simple equation: S/V equals 6 divided by diameter for a sphere. Nanomaterials are classified by how many dimensions are confined to the nanoscale. Zero-dimensional or 0D materials are confined in all 3 dimensions. These include quantum dots, nanoparticles, and fullerenes, typically ranging from 1 to 100 nanometers in all directions. One-dimensional or 1D materials have 2 dimensions in the nanoscale while extending to larger scales in one direction. Examples include nanowires, carbon nanotubes, and nanorods. Two-dimensional or 2D materials are confined in just one dimension, like graphene sheets and thin films that are atomically thin, but can extend for micrometers or millimeters in the other 2 dimensions. Three-dimensional or 3D nanostructured materials have bulk dimensions, but contain nanoscale features internally, like aerogels and metal-organic frameworks with nanoporous structures. Zero-dimensional nanomaterials are the workhorses of nanotechnology. Quantum dots are semiconductor nanocrystals, typically 2 to 10 nanometers in size. Materials like cadmium selenide or indium phosphide exhibit size-tunable optical properties due to quantum confinement. Smaller dots emit blue light, larger ones emit red. This has enabled QLED displays that surpass traditional LCD technology in color gamut. Metal nanoparticles like gold and silver exhibit localized surface plasmon resonance, where collective electron oscillations, create intense colors and enhanced electromagnetic fields. Iron oxide nanoparticles are superparamagnetic and used in MRI contrast agents. Fullerenes, particularly C60, are cage-like carbon molecules with unique electronic properties. Core shell nanoparticles combine different materials to optimize properties for specific applications. One-dimensional nanomaterials extend in one direction while being confined in two. Carbon nanotubes are the most famous example. They're essentially rolled sheets of graphene and can be single-walled or multi-walled. Single-walled carbon nanotubes are just 1 to 2 nanometers in diameter, but can be centimeters long. They have exceptional properties: tensile strength on the order of 100 times that of steel by weight, current carrying capacity per cross-section far above copper, and thermal conductivity comparable to or above diamond along the tube axis. The electronic properties depend on how the graphene sheet is rolled, making them either metallic or semiconducting. Semiconductor nanowires made from silicon, zinc oxide, or other materials are key components for nanoscale electronics and sensors. Metal nanowires like silver are used in transparent flexible electrodes for touchscreens and solar cells. Graphene is the poster child of 2D materials. It's a single layer of carbon atoms arranged in a hexagonal lattice, just 1 atom thick. Despite being the thinnest material possible, it has extraordinary properties. Electron mobility can reach the order of 200,000 square centimeters per volt second in suspended, high-quality samples, far exceeding silicon. Thermal conductivity is reported between roughly 3,000 and 5,000 watts per meter Kelvin, among the highest known. Mechanical strength is 130 gigapascals, stronger than steel by weight. Its isolation in 2004 earned Jaime and Novoslav the 2010 Nobel Prize. Beyond graphene, there's a whole family of 2D materials. Transition metal dichalcogenides like molybdenum disulfide have direct band gaps, unlike graphene, making them useful for transistors. Hexagonal boron nitride is an insulating 2D material. M-zenes are metallic 2D carbides and nitrides. These materials can be stacked to create van der Waals heterostructures with designer properties. Three-dimensional nanostructured materials have bulk dimensions, but contain nanoscale features throughout their structure. Aerogels are among the lightest solid materials known, with densities as low as 0.001 grams per cubic centimeter. They're created by replacing the liquid in a gel with air while maintaining the nanoporous solid network. This gives them exceptional thermal insulation properties. Metal organic frameworks, or MOFs, are crystalline materials with metal nodes connected by organic linkers, creating highly ordered porous structures. They have record-breaking surface areas, up to 7,000 square meters per gram, making them ideal for gas storage, separation, and catalysis. Zeolites are naturally occurring or synthetic microporous aluminosilicates used extensively in catalysis and water purification. Nanocomposites combine nanoscale reinforcements with bulk matrices to create materials with enhanced mechanical, thermal, or electrical properties. One of the most important characteristics of nanomaterials is their extraordinarily high surface-to-volume ratio. For a sphere, this ratio follows a simple formula: S over V equals 6 divided by diameter. This means as particles shrink, the fraction of atoms at the surface increases dramatically. Consider a 10 nanometer gold particle, roughly 1 atom in 5 sits at the surface. Shrink it to 2 nanometers, and most of the atoms are surface atoms. This has profound consequences. Surface atoms have fewer neighboring bonds and higher energy, making them more reactive. This is why nanoparticle catalysts are so effective. More atoms are available to participate in reactions. The high surface energy also lowers melting points because surface atoms can rearrange more easily. It increases dissolution rates, enhances adsorption capacity, and fundamentally changes how materials interact with their environment. Quantum confinement is the phenomenon where electrons are spatially confined to dimensions approaching their de Broglie wavelength. When this happens, the continuous energy bands of bulk semiconductors break into discrete energy levels, like electrons in a box. The Bruce equation describes the size-dependent bandgap of quantum dots. It has three terms: the bulk bandgap, a positive confinement term that increases with decreasing size, and a negative Coulomb term for electron-hole attraction. The confinement term dominates, so smaller particles have larger bandgaps. This is why quantum dots exhibit size-tunable emission. A 2-nanometer cadmium selenide quantum dot emits blue light around 450 nanometers. A 6-nanometer dot emits around 620 nanometers in the orange-red. Same material, different sizes, different colors. This tunability has revolutionized display technology and enables multiplexed biological imaging, where different-sized dots can label different targets. Nanomaterials exhibit lower melting points than their bulk counterparts, a phenomenon called melting point depression. This is described by the Gibbs-Thomson equation. The melting point decreases as particle size decreases because surface atoms have fewer bonds and higher energy. The effect becomes significant below about 20 nanometers and dramatic below 5 nanometers. For gold, bulk melting occurs at 1337 Kelvin. Below about 10 nanometers, the melting point falls steeply, and particles only a few nanometers across melt hundreds of Kelvin below the bulk value. This has practical applications. Nanoparticle-based soldering and sintering can be done at much lower temperatures, enabling electronics assembly on temperature-sensitive substrates. Conductive inks containing metal nanoparticles can be sintered at temperatures compatible with plastic substrates. Understanding melting point depression is crucial for predicting thermal stability during synthesis and application. The Schrödinger equation is a practical tool for estimating crystallite size from X-ray diffraction patterns. When X-rays diffract from a crystal, the peak width is inversely related to the size of the crystalline domains. The equation states that crystallite size, tau, equals k times lambda divided by beta times cosine theta. Here, k is a shape factor typically around 0.9 for spherical particles, lambda is the X-ray wavelength, beta is the full width at half maximum of the peak in radians, and theta is the Bragg angle. Larger crystals produce sharp, narrow peaks because many lattice planes contribute constructively. Nanocrystals produce broader peaks because there are fewer planes, leading to less perfect constructive interference. This provides a quick, non-destructive way to estimate average crystallite size. However, the equation has limitations. It only works below about 100 nanometers, it assumes no strain broadening, and it gives an average, not a distribution. For more accurate analysis, methods like Williamson-Hall or transmission electron microscopy are needed. Let's summarize what we've learned in this chapter. Nanomaterials are defined by having at least one dimension between 1 and 100 nanometers, and at this scale, materials exhibit unique properties not seen in bulk. We classify nanomaterials by dimensionality: 0D materials like quantum dots and nanoparticles, 1D materials like nanowires and nanotubes, 2D materials like graphene, and 3D nanostructured materials like aerogels and MOFs. The high surface-to-volume ratio, following S over V equals 6 over D for spheres, leads to enhanced reactivity, lower melting points, and increased catalytic activity. Quantum confinement, described by the Bruce equation, enables size-tunable optical and electronic properties. We've also learned key characterization equations: the Schrödinger equation for crystallite size from XRD and the Gibbs-Thomson equation for melting point depression. In Chapter 2, we'll explore synthesis strategies, both top-down approaches like ball milling and lithography, and bottom-up approaches like chemical vapor deposition and colloidal synthesis. See you there.